Remember in the case of electromagnetism, which was the motivation for everything, we considered the following. That if you have a quantum wave function, I can change the phase of the quantum wave function. Right? So that is one aspect. You change the phase of the quantum wave function. Secondly, in the Lagrangian, this combination appears always, P minus EA, and that leads to this combination in the derivative, that the derivative always comes together with IEA. Okay? Maybe there should be an H bar. There should be an H bar somewhere. Okay? And this you can call the covariant derivative. But then if you make this theta position dependent, then whenever you do this, the A has to be changed like this by a gauge transformation. We also learned that to use a concept we developed last time, if you take the covariant derivative and take the commutator of two covariant derivatives, we call that the curvature. And in the EM case, this is basically the field tensor up to a multiple, up to a factor, something like this. Okay? Because if you take the derivative of two of these things, it is the derivative, this guy acting on that guy. And under this kind of a transformation, F simply goes back into F. Because if you rotate the wave function, of course, the EM field does not change, right? EM field is purely physical. Under change of phase of the wave function, the E field and the B field, of course, does not change. All right. Now, what I want to do is to establish the analogous statements in the case of non-abelian gauge theories. And we are halfway there. I just want to give you an overview before continuing with the derivation. So instead of a complex number, which is a wave function, the wave function is now a column vector, say red, green, blue. All right? Rank 3 column vector, if you're talking about SU3, in general, a rank n vector. I now do a general unitary transformation under SUN. The most general SUN transformation can be written in this form, e to the I theta times t, where, of course, the exponential is an n by n matrix, because I am doing a transformation on a column n vector. A unitary n by n matrix can be written as e to the I something, where in the exponential you have a Hermitian n by n matrix. And a Hermitian n by n matrix can be expanded as a linear combination of the basis matrices. And the TAs are the generators. All right? They are n square, or n square minus 1 if you are talking about SUN, independent n by n Hermitian matrices. And the theta A's are the parameters. So this is the analogous statement to this one. Okay? Now, last time we had established that under this kind of transformation, then when you want to displace a vector, this is the operator you have to use, where gamma mu is an n by n matrix. This simply reflects the fact that when you move from a vector from one place to another, you have to account for the change of the basis vectors as well. The change of basis vectors would mean that the components gets mixed up, and the mixing of the components is represented by this n by n matrix. Gamma, if it is an n by n matrix, can again be expanded in terms of the basis matrices. And the coefficients I call A super A. All right? And just to align with this expression, I take out a factor, I don't know what the minus signs, IG over H bar, where G is a parameter analogous to E. It's the coupling constant. All right? So now we have, instead of one vector potential A, we have n squared minus 1 vector potentials. The vector potential carries two indices. The index A is an internal index, like red-blue, red-green. It has n squared minus 1. And then the mu is a space-time index. All right? So I think that's roughly where we were at last time. We have introduced n squared minus 1 vector potentials, okay? Or gluons. Now, today I want to develop the analogs to these statements. The first statement is under a coordinate transformation like this, where theta is position dependent, what happens to gamma? What is the analogous statement for this? Okay, A is simply gamma. Okay, the analog of A would be gamma. What happens to the connection 1 form under a coordinate transformation? I can either write this in terms of gamma, or I can write this in terms of A. Okay, if I know how gamma transforms, then I know how this transforms. Okay, think of this as it is a matrix, but you can also think of it as a vector in the space of matrices. And these are the basis vectors, and these are just the components. So I can either write this as a transformation on the vector, or I can write it as a transformation on the coefficients. I will only do the former. It's notationally more compact, but it's the same thing. Secondly, I want to develop an expression for the field tensor F mu nu. Okay? It actually will take a form slightly more complicated than this. How does the analog of the E field, B fields depend on the vector potentials? And also, under this kind of a transformation, what happens to this field? Oh, there is one other thing. That is here, the Lagrangian is minus 1/4 F mu nu, F mu nu. What is their analog here? Now, what can you guess to be analog here? The last is not on the PowerPoint slides, but I shall briefly go through them. So if we have all these things, we would have a complete analogy between EM, which is a simple case of one single degree of freedom, U1, and the case of non-abelian phase theories, which is a generalization of all these ideas to non-trivial internal symmetry, SUN. All right? So that is the overall picture that I will try to describe today, and I'm pretty sure I can finish this in half today's time, and then we shall go on. So let me back off to where we were last time. So to start with non-abelian gauge theory, just to review a little bit. We will take the example of SUN, say n being 3, representing the 3 colors. So the wave function is a column vector of n components. Okay? And I consider transformations on this column vector of this form. This is the most general unitary transformation on these column vectors. And if I exclude the identity here, then I'm talking about SUN, the special unitary group. Okay. So if you go back here, let's see. We had discussed earlier the concept of gamma, which is an n by n anti-Hermitian matrix. This comes about because when you push something, you have to do a coordinate transformation as well. And in the EM case, we notice that gamma mu is related to the vector potential. So here, gamma mu, which is a matrix, is also represented in terms of the vector potentials, where now the vector potentials carries this internal index. Okay? So as many little a's as there are basis matrices or generators T sub A. So there are the n square minus 1 gluons. I think that's where we were last time, I think. So there are n square minus 1 photons or gluons. Did we do this last time? No. Okay, so that's where we were. So I just repeat this statement. Gamma is given by this. Now I want to calculate, I do this first, calculate the curvature tensor. The curvature in general is given by this expression. Is the antisymmetric derivative of the gammas plus the commutator between the two gammas. And in analogy with this expression, now this is an n by n matrix. I always expand it in terms of the basis matrices, so that for any expression, I can either talk about the matrix or I can talk about the components. the expansion coefficients. That's just a change in the language. So in exactly the same way, this is an n by n matrix. So I also expand this in terms of this basis. And the coefficients I call FA. All right? And I just carry these coefficients in front. So this expression is meant to be analogous to that one and defines F. All right? Because any matrix can be expanded in terms of TA, and that defines the expansion coefficients. And as a matter of convention, I pull out the factor IG over H bar. Now, I haven't completely proved everything. There is one thing you need to check, which I have not explicitly done for you. I think it should be straightforward, because you have to convince yourself that R mu nu is traceless. Okay? If it is, it's an n by n matrix. If it is traceless, then the expansion does not involve T0. Okay? That is, of the n square matrices, you don't have to take the 0 one. And also, you have to check that it is anti-Hermitian. I think that's okay because, let me just check the anti-Hermitian for you. If this is anti-Hermitian, you take the derivative, it stays anti-Hermitian. That's okay. You have two anti-Hermitian matrices. The product. Now, if I take the Hermitian conjugate, then you get two minus signs. That's okay. But in the Hermitian conjugate, you also reverse the order. So this, again, acquires a minus sign. So the whole thing is anti-Hermitian. And so if you take out the I, the rest would be Hermitian. And so the FA would be real. Okay? Just like the AA would be real. Okay. And the traceless property actually is also straightforward. Because this one is traceless, the trace of a commutator is always 0. Because trace of AB is equal to trace of BA. So what I next want to do is to find an explicit expression for F, right? Which is analogous to this one. I want to find an expression for F analogous to this one. Which, this one, think about it, because there's a danger that everything is too abstract and you lose sight. This expression is really the analog, is really a compact way of writing these. That B is equal to curl A and E is equal to minus d phi, gradient phi minus dA dt, right? These are things you learned in, I don't know, second year EM. And this is just a compact way of writing these. Now I want to find the analogous expression on the side. How the fields are related to the potentials. So I start with the definition of the curvature tensor. Remember, the curvature tensor is just the commutator between two D's. All right? And this is, if you write it out, this is equal to d mu gamma nu minus d nu gamma mu plus or minus, plus the commutator, gamma mu, gamma nu. Okay? So I just write this out here. So it is, where's the cursor? Yeah. D mu, gamma nu. I just expand gamma nu in terms of the matrices, TA. D nu, gamma mu. All right? And then a commutator between gamma mu and gamma nu, where I have expanded each in terms of the A's. So there are two overall coefficients. This first A and this first T combine to form gamma mu. And this second A and this second T combine to form gamma nu. And all the commutators occur because of the T's. Okay? The capital A's are just numbers. The T's are matrices. Is that okay? I don't know whether you are confused by the notation. Maybe I should use a different notation for matrices. I don't know, script letters or something that may help you look at it. But remember, on the right-hand side, the only matrices are the t's. Everything else are numbers. Okay? So when I do this commutator, this is what I get. Any questions for the first line? I think you probably need to go back and do a bit of derivation yourself to follow it through. All right, so let me take out one factor, Ig over h bar, and see where's the rest. Now, look, these two, first of all, they both contain a factor Ta, so let me take it out. So I have del mu A nu minus del mu A mu. So we have this bracket. This bracket is very much like EM, right? This is just like the curl. Curl, or the anti-symmetric derivative of the vector potential. But now there is an extra term that comes from the commutator of the two t's. So let's write out what this is. So TATB is I FABCTC. That's the definition of the structure constant. I think we discussed this before, right? Well, that's really not saying anything, because TA commutator TB is another matrix of the same type. If it's another matrix of the same type, I can always write it as a linear combination, some coefficient C multiplied by TC, sum over C. Okay? And that is the definition of the structure constants. Now, there are some homework problems for you to prove some of the properties of F. Okay? For example, that is totally anti-symmetric and so on. And in fact, if you go back to the case of SU2, F is just epsilon. Epsilon ABC, the totally anti-symmetric symbol. Okay? So now let's see what happens to this term. First of all, there is this I and this I. Now, no, I have, let's be a bit careful about signs. So now this term comes with two such factors. I have pulled out one, so here's the other one. Okay. Now, so these two i's together gives me a minus sign. Now, let me see what next I want to do. I want to pull out an overall factor of TA. Maybe okay. I want to pull out an overall factor TA. So if I change that TC to TA, then I would be able to pull out the TA outside here. Okay. What I want to do is to change this TC to TA, then I can bring it out. Now, how do I do this? It's very simple. I have three indices, A, B, C here, and they are all summed. Okay? They are all summed. They are all dummy indices, so I can change their names. So if I change C to A, in fact, just do a cyclic permutation on these three. Okay? C becomes A, B becomes C, A becomes B. Under cyclic permutation, F doesn't change. Okay? So TC becomes TA, A becomes B, B becomes C. That's what I have done. All right? Because F is unchanged under a cyclic permutation ABC, I just do that permutation. F doesn't change. TC becomes TA, which I pull out. Then this A becomes this B, that B becomes that C. If I pull out the TA, then everything else I recognize as FA. Okay? Because the F or the R is a matrix, and it is, if you go back, perhaps it's, R is a matrix which I expand in TA, and the coefficients I call FA, right, apart from this factor. So once I do this, I recognize I get the formula for FA. So two remarks. The first is that the field tensor now has an extra index. In EM, F mu nu has two indices, both space-time indices, that is, indices in base space. Now, in non-abelian gauge theory, F mu nu has three indices. The upper index in internal space, right, goes from 1 to n squared minus 1, and then mu nu in base space. Right? Now, I have been careful to always label the names of these indices by different types of letters. Space-time indices are all, in base space are always mu nu. Indices associated with the vector are always ijk. And indices associated with how many different matrices there are always ABC. These goes from 1 to n squared minus 1. These goes from 1 to n. Okay? And mu nu goes over the dimensionality of the base space, which can be totally different. So we have this expression. So the first thing is that the field tensor, now there are, in the case of SU3, 8, you can think of 8 EM fields, 8 electric fields and 8 magnetic fields, if you like. But the electric and magnetic fields are not simply given by the curl of the vector potential. But there is another term which depends on the strength of the coupling constant. If the coupling constant is very small, for weak fields, oh, by the way, I have to go back and tell you one more thing. Look at, say, this expression. Oh, go one back. This is how we define the vector potential A. Now, it always comes in the combination G times A. That combination always comes together. And in fact, it's actually, although you don't think about it too much, that's true also in EM. Always a combination little e times A in EM. That combination always appears together. I can always shuffle the coefficients. Okay? I can multiply little e by a certain constant and then divide the vector potential by a constant. That doesn't change anything. Okay? You are used to the fact that E is a fundamental constant. It's something that has to be chosen. I will come back to this later because I don't want to interrupt this flow. I just want to tell you now that E times A is actually one physical thing. Separating the two is just a matter of convention. Here, G times A is one thing. Separating the two is to some extent a matter of convention. Okay, so whether you say it is G is very small or A is very small is to some extent the same thing. So for weak fields, if the field is weak, then this term doesn't matter. And you would have just like EM, but EM for each gluon independently. There are 8 types of gluons, 8 or in general n squared minus 1. For weak fields, each type of gluon behaves like a photon, satisfies an equation just like Maxwell's equations. Okay, so you have 8 independent Maxwell's equations. The red-green or red-green bar gluon satisfies Maxwell's equations, where the source of that is some red-green bar charge. You can write down equations like these, Gauss' law, everything, you know, Faraday's law, everything, 8 different ones. But if the field is not weak, or the coupling constant is not weak, then there is a nonlinear term. The relation between the field tensor and the potential, A becomes nonlinear, and secondly, the different colors will mix. All right? If you have little a is number 1, then it also involves the other 7 vector potentials. And that is why the theory is much more complicated in the end. All right? Now, I'm not going into the solution of these things. Not many people actually work on the classical theory, this classical theory. The interest actually is in the quantum theory. So to really take the next step, you have to learn about the basics of quantum field theory, as I said last time, the Dirac field, the Dirac equation, and so on. And that's really another course in itself, which I won't go into. Here, I simply mentioned that that is the case. All right, so that is the expression. Now, you see, you probably could not have guessed this structure without this formal apparatus of covariant derivatives, this transformation of the vector potential, the idea that you can have different bases in different places and so on. Right? This is something that would have been rather difficult to guess, but it becomes quite natural once you adopt this formal language. All right? So that is, so we have done this. Okay? So just some schematic that F is nonlinear in the potential. So schematically, F goes like the derivative of A plus G times A times A. Oh, by the way, for those of you who have learned relativity, you know it's the same thing for the curvature tensor, right? The curvature tensor is nonlinear in the Christoffel symbol. Okay. Now, I come to this statement, that the Lagrangian schematically goes as the square of the field tensor. So it goes as derivative of A plus GAA squared. So if we expand it, it goes like this. Now, I will amplify this statement in a little while, in case for those of you who are not familiar with this way of formulating electromagnetism. Okay? So it goes like this. And so the Lagrangian takes that form. And here I'm just being schematic. You probably don't know about how Lagrangians connect to field theory. But roughly speaking, a term like derivative A square goes like a Feynman diagram with a line like this. It's just a propagation from one point to another point. A term with three A's, right, this is 1, 2, 3, looks like a vertex. It's three lines coupling together with a G, and a term that goes like this is a 4-point vertex. So that means, in terms of Feynman diagrams, you will have these interacting vertices. This one meaning two gluons hitting each other to become a third gluon. These are gluon-gluon scattering to become gluon-gluon. So gluons are interacting, right, in quantum field theory. And that is why non-abelian gauge theory or quantum chromodynamics is so complicated. G is also not small. Okay? G is also not small, so you can't really do this perturbatively. Normally, in QED is also not all that trivial. But typically, we expand in powers of E. In practice, that is just a fine structure constant, 1 over 137. So that series, you know, it's a good series. For example, if you calculate the anomalous magnetic moment of the muon, that is now carried to 6th order. So you are expanding in powers of alpha. Right? 6th order, I think, means alpha cubed. Okay? Yeah, probably means alpha cubed. And it's now checked experimentally to, I don't know, 12 digits or something. But G is not small. Normally, G is of order 1. Right. Now, there is another story that G is actually a function of the distance scale. That is called renormalization group. That's another long story, which I won't go into. But at ordinary length scales, ordinary, I mean ordinary nuclear length scales, nuclear distances, 1 femtometer, G is of order 1. So the perturbative series is not very useful. And because it's nonlinear, it is very difficult to solve. So there is not much known about non-abelian gauge theories in detail. Much more difficult than quantum field theory because it is nonlinear. So non-abelian gauge theory is a nonlinear interacting theory. The gluons interact with each other, whereas, remember, photons do not interact with each other to a very good approximation. If you have two photons coming together, they don't scatter. Okay? To say photons do not scatter actually is the same statement as something you learned even in high school, that in EM there is the principle of superposition. Okay? So if you find one solution, you find another solution, adding them gives you a third solution. That is not true in non-abelian gauge theory. That is also not true in general relativity. You cannot say I find all possible solutions and then I expand in terms of those solutions. Right? That doesn't work. Principle of superposition doesn't work. Okay? So that's why it is so much more complicated. Okay. Now, before I do this, I want to go back and talk about the Lagrangian, because I realize that may not be familiar to all of you. I want to talk about the Lagrangian and how that relates. So I think I have just about, I'm going to erase most of this, but just remember we still have to do two things. The analog statement, under a rotation, what happens to the connection, which is this statement. Right? That is what I'm going to do next. And then what happens to F. Right? But I'm running out of space, so let me just erase. Let me try to derive the Maxwell's equations for you in just a few lines by starting with the Lagrangian, or rather the Lagrangian density. So the action is the time integral of the Lagrangian, and it is the four-dimensional space-time integral of the Lagrangian density. Okay? And the Lagrangian density I write in the following way. So this is the four-dimensional Lagrange integral of F mu nu times F mu nu. Well, the Lagrangian density has to be a Lorentz scalar, right? Because the action is a Lorentz scalar. Because I minimize the action, I must give the correct answer. So whatever I minimize must be the same. You give the same answer as me. D4x is a Lorentz scalar. It is, if you rotate in space-time, d4x remains invariant. So the Lagrangian density is also a Lorentz scalar density. If I want equations that are linear in the end, then I want a Lagrangian that is quadratic. Right? You vary a quadratic thing, you get something linear. So the Lagrangian density, I want something that is quadratic in the fields, and that is a scalar. So it is not difficult to guess it should be F times F. And if I do this, I eat away all the dummy indices. That's invariant quantity. Now, the coefficient in front turns out to be -1/4. And you can put some constant here. I will discuss that constant later. Okay? Now, that is sort of like E squared, B squared, right? So if you vary this, you will get E delta E, which has to be 0. And so it must be something E equals 0. That will give you homogeneous Maxwell's equations. But of course, Maxwell's equation is not homogeneous. It must come with the current. So I must add a current, okay? So another term I can add is this, okay? The current, the four current times the vector potential. I think that is about right. And the current is actually like this. The current for a single charge is E. What? No. Okay. So let me try to now do the variation. So what is this equal to? So this is -1/4. -1/2. I still have the K. F mu nu. Because I have two of them, all right? So I vary just one of them. I will have a factor 2. F mu nu, remember, is del mu A nu minus del nu A mu. All right? So let me... Okay? So that is the variation. And then here I have delta A mu. Let me use a different set of brackets here. So I'm varying the four-vector potential. It goes like this. Now, I'm doing it just off the top of my head. I don't guarantee to get the minus signs right. But it doesn't matter for this course. So as usual, I do the integration by parts. But before I do so, I notice one thing. This is anti-symmetric in mu nu. This is anti-symmetric in mu nu. So if I just keep one of these two terms, the other one will be the same. Okay? So what I'm going to do is I'm going to, let's see, kill this term and kill that too. I integrate by parts. That means I can take this del nu here and change the sign. All right? So what am I going to get? I'm going to get d4x. Oh, sorry. Let me keep the color convention. I'm going to have d4x. Everybody will have a delta A mu. So I take that out. Okay? Because once I integrate by parts, every term will have a delta A mu. And the rest here, what do I have? Minus, minus, minus. So 3 minuses, del nu, f mu nu. And here I have j mu. And here is a 1 over k. Okay? So I have up to some signs, del nu, f mu nu is equal to k times j mu. And this you should know, now, this is really 4 equations, okay? And one of them will be, perhaps I should write it out. Del nu, let me take the mu equals 0. So del nu f0 nu is k times. J0 is just the charge density. Okay? So you write this out. This is d0 f0 0 plus di f0 I. This is 0. There is no f0 0 because f is totally antisymmetric. And f0 I is just the I component of the electric field. So up to minus signs, which I am, so this is like divergence of E is k times rho. All right? So that's Gauss' law. And if you look at the other 3, they are just Ampere's law. And this is actually a nice way of deriving Maxwell's equations, or at least understanding the structure of Maxwell's equations from a very simple Lagrangian. This is sort of a very natural thing if you require a term that is quadratic in the fields and a term which is linear and coupling to a current. So this is something you could have guessed more or less, whereas this, in particular, Ampere's law, is something that you may find a little bit more difficult to guess. Okay? And this is a very simple understanding of Maxwell's equations. Maxwell's equations, I think in the last analysis, we understand it in these terms, it is much more natural. And the point really is, if I want to go to EM, go to gauge theories, all I have to do is really do something roughly like this. Imagine there are 8 different gluons labeled by the index little a, and just sum over the little a's. And there will be 8 different kinds of currents, and you sum over them. Then that is the starting point. And the theory that emerges is whatever emerges. Now, of course, if I start with this, the next few derivations are not right because, for example, this f is not just this term. There is another term, a nonlinear term here. Okay? And therefore, the equations will be much messier. And when you write those down, they look rather complicated, long things. But in terms of this, it is okay. All right? Now, one point I mentioned is that E and A come together in the following sense. If you look at this Lagrangian, the two terms, the F goes like A, right? So it goes like A squared plus EA. One over K, A times A. So if I just change A into 2A and so on, all right? And this is proportional to the electron charge. So electron charge times A. So now, the 1 over K doesn't really matter. I can pull out an overall factor 1 over K. So this is like A squared plus KE times A. Okay? Because in the action, if I multiply the action by an overall constant, that's irrelevant because I'm only seeking the minimum, right? If your action is 2 times my action, your equation of motion and mine would be the same. Okay, so the overall factor does not matter. So I can always scale out an overall factor. That does not matter. And you see K and E appear together. So changing K is the same as changing E. And if you look at this final equations, that is exactly what happens. It's just a matter of convention. When you first learned EM, what is the value of K? 1 over epsilon 0. That's the MKS units. In advanced EM books, what is the value of K? It's 1. That is CG or rationalized CGS units. In some books, it is 4 pi. All right? There are actually 3 common sets of units in common use. 1 over epsilon 0 is the MKS units. Is what all the undergraduate textbooks use. That gives you measures charge in coulombs. Okay? If it is, let me think. If it is 4 pi, that is what's used to be called the CGS units. And the unit of charge is the ESU, electrostatic units. When I was a high school student, my high school textbook was in ESU units. In ESU units, the Coulomb's law goes like this, E1, E2 over R squared. Now you learn there's a factor here like this, right? So if you choose, if epsilon 0 is 1 over 4 pi, you would get this law. Okay? So that is choosing K equal to 4 pi. There is another third choice, which is often used where K is chosen to be 1. And they're just different units of charge. Okay? So changing the unit of, that is just a convention on the unit of charge relates to this factor K, right? And that always means that really the factor EA occurs together, all right? And it sort of appears here, you know, if I scale A, I can compensate by E, and then in this term I compensate by K. That is what happens. Okay, that's why, and that's why in non-abelian gauge theory, sometimes people use the convention that little g is equal to 1. They just don't bother to write g because g times a always appear together. So they use a convention where little g is equal to 1 just to save some writing. Right? Now, why can't we use a convention where capital electric field is equal to 1? Because we have a convention as to what is the unit of charge, 1 coulomb. In non-abelian gauge theories, if you don't need to stick to any convention about what's the unit of color charge, then you can simplify some of your equations by dropping the g. So in some textbooks, especially the more theoretical textbooks, you will not see the little g, just simply the a. Right. All right, so that's an aside. Okay, so let me now talk about the change of basis and rotations. Now, this part is mathematically a little bit more involved, and I will try to go slowly, but I suspect you would need to go back and work through it a bit yourself. I want to discuss what happens under a change of basis to the connection, and then to the curvature, and then I want to check the consistency between the two. Now let's see what happens. Let me start with the connection. Now, this is slightly complicated and involves 4 vectors. So let me try to explain rather carefully what's going to happen. let me recall what is the connection. The connection occurs, let me stick to this convention over there. You have a vector, and you want to parallel transport to this vector. They really should be the same length. They may be different directions, but they are the same length. To this vector. You push this vector over to here. That requires that you have a connection, right? So the connection relates these two. So when you push it, the connection tells you what little bit you need to rotate. Okay? It tells you how the basis vectors has changed from x to x plus delta x. The connection represents the relationship between two neighboring vectors which are parallel transported. Is that okay? Now, I do a change of basis. So this is x. The vector space at x, this is the vector space at x plus delta x. I rotate the axis here. Now, another way of thinking about it is that I rotate this vector. Same thing, right? So I rotate this vector, so I need a different color, to this green vector. So this is an angle theta abstractly. Okay? I also do a rotation here, which is a different angle theta. Okay? Now, having done the rotation, I want to ask what is the connection now? The new connection. Okay? Do you understand? The connection one form, the original connection one form gamma, does a parallel transport from this black vector to that black vector. Now I do a coordinate dependent rotation. First black vector becomes first green vector, second black vector becomes second green vector. The new connection takes the first green vector to the second green vector. You understand? So perhaps I draw it another way. So you have the black guy here, the black guy here, and the green guy here, and the green guy here. So the original gamma is this one. The new gamma is this one. Okay? And this is the rotation, which is essentially e to the I theta of x. This is the rotation e to the I theta of x plus delta x. Schematically, all right? I haven't written things down in great detail. So I want to find the expression for the new gamma. That is what I mean by the transformation of gamma under a rotation. Right now, because this is more complicated than things we have done before, because this involves 4 vectors. Now, everything we've done before involves only 2 vectors. You parallel transport one vector to another vector, right? Or you rotate, do a rotation, then this vector becomes this vector. But I'm now combining the 2 concepts. One is a rotation, taking a black vector to the corresponding green vector. One is a parallel transport going from x to x plus delta x. I want to combine these 2 concepts together. And in doing so, I will be able to answer the question, what is the new gamma? After I do the rotation of axis, I must have a new gamma. How is the new gamma related to the old gamma? The new gamma takes this guy to this guy. The old gamma takes this guy to this guy. Do you understand the concept? I mean, never mind the formulas. That will come later. More important for you to have the concept. That is what I mean by the transformation of the connection one form under a rotation of axis, under a coordinate rotation. All right? Once you have understood the concept, the formula is very simple. So the rotation taking black vector to green vector means an operation like this. Psi going to something times psi, where this is a rotation operator. In SUN, this operator is e to the I theta times t. Theta are the parameters, t's are the generators. And the position dependence is now completely hidden in theta. Okay? T are just constant generators. They don't carry position dependence. So this tells you how to go from black to green. Now, how do I go from green, first green to the second green? Answer is very simple. I go from the green to black here, take black to black over here, and go from black to green here. In other words, if you look at this picture, how do I get this? Then I do this. Right? That gives the result. So how do I express that algebraically? If the transformation from black to green is e to the I theta t, then the green back to the black is e to the minus I theta t. Right? This first factor takes the first green to the first black. First black to the second black is just the usual covariant derivative. The gamma is hidden in the D. Okay? D is normal derivative plus gamma. This is the operator with the original gamma that takes you from the first black to the second black. Then from the second black to the second green, I do the positive rotation, but using theta at the new point. Notice these two have minus signs and also differ because the theta is evaluated at slightly different points. And these three factors just corresponds to these three arrows. The first one in reverse, that's why there's a minus sign in the exponential. Then this push, and then this one. Is that okay? So those three factors is the mathematical expression of this picture. Once you understand this concept, the rest is just straightforward computation. That's just algebra. Right? It's more important for you to understand the idea. The algebra you can work through. I mean, you can do the algebra better than I can. But what you need to understand is the concept. And of course, I only evaluate this in the limit where delta x goes to 0. Okay, so let's see what happens. So I have this product of three things. And to save some writing, instead of writing theta ATA, I write that as simply T. Okay, that's just to save some writing. And also, I will go for the case where theta is also infinitesimal. Now, in this calculation, there are two things which are infinitesimal. One is that the displacement is infinitesimal, delta x. The second is that each little rotation is also infinitesimal. Okay? Because that's all I need to understand. Once I have understood an infinitesimal rotation, I can build it up to a finite rotation. Okay? So there are two things which are infinitesimal. So in fact, the thetas are infinitesimal. Instead of writing theta ATA, expanding it out, I just write T of x as an infinitesimal matrix. So the first line becomes the third line, just to make things easier. Okay? So you have something quite compact. E to the minus IT, e to the IT at a different point, e to the minus delta x times d. So let's just expand everything. So this factor is 1 plus I times this t. But this t, I also expand in delta x. So it's t plus delta x times derivative of t, where the t without any notation is evaluated at x. Okay? This t is the same as that t. Is evaluated at x. So I do two expansions in the first factor. One is I expand the exponential using the fact that t is small. Then I expand t using the fact that delta x is small. The second factor is using delta x is small, it's just 1 minus delta x times d. The third factor is 1 minus it. So let's look at this. You know this has to give you just the identity if delta x is 0, right? If delta x is 0, that means this is 0. Then you just go up and go down, right? And the result must be identity. So you know everything must be proportional to delta x. In other words, the terms without delta x must cancel. Now, what are the terms without delta x? It's only this one, it, and this one minus it. When you multiply out, those are multiplied by 1, and they cancel. Okay? So the terms without delta x have to cancel, and that you could have guessed from the beginning. Everything else now contains a delta x, which I pull out. So what do I have? With the delta x, there is a d. Then there is also a term which goes as t times d, and a term which is d times t. Okay? One term which is t times d, one term which is d times t, and they come in with opposite signs. Because the rotation, one is a minus sign, one is a plus sign. So you have a term which is t commutator d. And then there is this term, which is the derivative of t. All right? Now, I leave you to work out the i's and minus signs and so on. So there are three terms. One is d, one is t commutator d, one is derivative t. Right? So you work out for these infinitesimal transformations. So we find, of course, this whole thing. What happened? No. Yeah. Of course, I want to interpret this new bracket as the new d, right? Because the transformation is always defined by this guy, right? So I want to write this whole thing as e to the minus delta x nu d. And therefore, the braces will be just a nu d. So under this transformation, d goes into the thing on the right-hand side. But by definition, d is just the normal derivative plus gamma. So if I just put this into here, then I find the new gamma goes into the new gamma, where the new gamma is the old gamma plus I t commutator gamma minus I derivative t. Derivative t, yeah. Okay? So that is the transformation law for the connection one form. So I just write it out again. Gamma goes into gamma plus I t commutated gamma minus derivative t. Now I want to emphasize one point, and that is this is a nonlinear transformation. The last term is nonlinear in the following sense. You see, the first two terms are linear in gamma. Just take the simplest case. If I multiply gamma by 2, the first two terms gets multiplied by 2. In particular, if I start gamma being 0, and if I have a linear transformation, then after the transformation, gamma stays 0, right? Suppose the last term is not present. Suppose I have gamma equal to 0. I do a transformation. If you have just the first two terms, the new gamma stays 0. So linear means, just take the special case, that 0 maps to 0. But no, this is nonlinear. 0 can map to non-zero, right? If gamma is initially 0, but you do a transformation where the t is not constant, the new gamma is non-zero. For those of you who have studied relativity, remember the statement in relativity that the Christoffel symbol is not a tensor. Although the Christoffel symbol has 3 indices, it is not a tensor in the sense, you remember a tensor means that how shall I write it? A tensor, say the curvature tensor, that is a tensor. So under a transformation, that is simply multiplied by a bunch of transformation matrices, right? If there are 4 indices, there are 4 transformation matrices. So if R is initially 0, under a transformation, it stays 0. Right? Remember, in relativity, we have an important concept, that R being 0 is an invariant statement. And that invariant statement corresponds to the fact that space-time is flat. That is a statement which is independent of the choice of coordinates. Because if you change coordinates, and not even linear change of coordinates, you can change to curvilinear coordinates. General changes in coordinates, it transforms like this, which is a linear transformation. So if R is equal to 0 in any coordinate system, it stays 0 in all coordinate systems. That is because it transforms linearly, and I will come to this in a minute. But gamma does not transform linearly. So gamma, in general relativity, you have learned that under a transformation, it does not go like this, even though it has 3 indices. So you can have gamma being identically 0 in one coordinate system. Under a transformation, it becomes non-zero in a new coordinate system. So to state that gamma is equal to 0 is not an invariant statement. It is not a statement about the space. It is a statement about the coordinate system. Okay? Same space, I draw 2 different coordinate systems. In one case, gamma is 0. In another case, gamma is not 0. That statement is deeply related to this fact that gamma does not transform linearly. Okay? So you can transform from 0 to non-zero. And the reason, the deep reason behind this is, look at this picture. Gamma relates 2 points. Gamma is an object that relates 2 neighboring points. Okay? So if the 2 rotations are different, originally gamma equal to 0 means I don't have to rotate these 2, right? I mean, you think about it physically, it's actually very clear. Gamma means how you take this to this. Okay? Gamma equal to 0 means these 2 are the same. When you transport a vector, you don't have to mix up the components. So gamma equal to 0 is a statement that this is the same as this coordinate system. But if I now do a coordinate dependent transformation, I do this, but this. Then to go from here to here, obviously I need a non-zero gamma. Okay? Because it relates 2 points. 2 different points. At the 2 different points, you can do 2 different things. And therefore, what was originally a trivial relationship, gamma equal to 0, becomes a non-trivial relationship, gamma not equal to 0, because it relates 2 different points. And that's where the nonlinear thing comes from. And this interpretation, you see, makes sense because the nonlinear term depends on the derivative of t, namely the difference between this transformation and this transformation. Okay? If these 2 transformations are the same, then originally trivial transport still becomes trivial transport. Okay? So it is nonlinear because of the difference of the transformation between the 2. Is that okay? So I just want to, these formulas are a little bit messy, and what I have written down, by the way, is the matrix representation. You can also write this in terms of the components. You see, because remember the following, that gamma as a matrix is really Ig over h bar A times t, right? And t is actually theta times t, right? So you can write all this out in terms of the components. So let me just write this. So Ig over h bar A mu Ta goes into Ig over h bar A mu Ta plus I theta At, well, I shouldn't call it theta A, theta BTB. And this gamma is Ig over h bar A mu Ta minus I d mu. So d mu of x only on theta A. Okay, it goes like this. And if I pick out the coefficient of TA, pick out the coefficient of TA. Now here I have to be a little bit more careful. Let me just do this. I pick out the coefficient of TA. Here I have to be a little bit careful. Let me do not even call this A. I call this C. That's a dummy variable anyway. So this term goes like I times IG over H bar theta B AC. TBTC is IFBCA TA, right? So I cancel this. And I also drop this factor. This I is outside. Then what do I get? I get A goes into A minus FCBA theta BAC, and then minus 1 H bar over G d mu of theta A. Okay, goes something like this. This is the analog of the statement in EM that A goes into A minus H bar over E derivative of theta. This is the gauge transformation that by now you are familiar with. In EM, there is only one A. Okay? When you rotate the complex angle, then at the same time you have to do a gauge transformation on the A's. By the way, this is also nonlinear. And it relates to the following fact. To say A is equal to 0 is not a physical statement. It is not a statement purely about the physics. It's also a statement about the gauge that you choose. Because if there's no EM field here, you can say A is equal to 0. I can say A is not equal to 0. A can be just this term. Okay? But now we have N, say 8 gluons. Under a gauge transformation, it goes like this. This term is similar to this term. But there is now the additional terms where you have essentially theta cross A. This is schematically like theta cross A in terms of the ABC indices. Right? Think of FCBA as like epsilon. This is like a cross product. Okay? So this is the generalization of this statement. And in fact, the fact that it is nonlinear is not new. Even in the EM case, it is nonlinear. Any questions? So I have it here. So just go back to this case. This is a general expression for the transformation of gamma. In the EM case, gamma is simply I, a coefficient times A. It's a 1-by-1 matrix. And T is theta ATA, but in this case, TA is just the identity, so there is only one theta. You put this in here, the commutator is of course 0 because you are dealing with 1-by-1 matrices. So you just have A mu, and then this derivative is just a derivative of theta. So that is the familiar formula. All right? Again, the formula above would be relatively difficult to arrive at if you did not have this picture of relating different vector spaces at x and x plus delta x. So this is just a gauge transformation of the potential in EM, all right? Which is where we started this whole business. The fact that the phase of the quantum mechanical wave function and the gauge degree of freedom in EM are related. That is this formula. We have now generalized this formula to the case of gluons, not just one photon, but 8 gluons. That is the corresponding gauge transformation. Okay? Yeah, yeah, please.
At the beginning of the class, you said if there is coupling, so there will be some nonlinear terms in the expression of R or gamma, etc. And is it possible to add some this kind of rotation to the system so that the nonlinear terms cancelled?
Good question. In general, of course not. In general, no. In very special cases, of course, yes, because it's very simple. Take a case where even A is identically equal to 0. No vector fields. There certainly is no nonlinear terms, not even linear terms. But I do a transformation like this. Then A becomes non-zero. If A is non-zero, then the nonlinear terms will also be non-zero. So I ask the reverse question. You can have a case where the nonlinear terms, you just construct a case where the nonlinear terms are 0. Okay? But then by doing a gauge transformation, I can make it non-zero. I ask the reverse question. It's easier to construct an example. Right? All the nonlinear terms comes with the. Let me go back. I think I can answer that question rather more carefully. Look at that term. All right. Suppose I choose the vector potential to have only one color. That is, capital A. There are 8 indices, right, for the little a, say SU3. I choose it only have to have the one component. Let me choose this. Okay? Then, of course, the last term will be 0. Because F, A, B, C, A and B have to be different. The little a and the little b, because they're anti-symmetric. Right? So if capital A points only in one direction in color space, to put it heuristically, has only one component, then that term will be 0. And you don't have that nonlinear term. Okay? Now, to say it points in only one direction is a highly non-trivial statement because it has point to one direction everywhere. But in some sense, this sort of question is not very, very relevant for the following reason. In EM, we deal a lot with classical EM. Okay? So you look at the field and so on. But in QCD, there's not much point in dealing with the classical theory. You are dealing with the quantum theory. In quantum theory, you are not free to say what the wave function is, what the field is. It just take on every possible value, right? And you just have to sum over all possibilities. Do you see what I mean? Just like in classical physics, say x, you can say I force x equal to 0. But in quantum mechanics, x fluctuates. The wave function covers a range of x. You are not free to say what x is. So in the quantum theory of these A fields, I don't specify what A is. A is an operator. Okay? So I can't choose something for the operator to be 0. Okay? So if you deal with classical things, there are some mathematicians who go in the business of finding classical solutions to these Yang-Mills equations. In those cases, there may be special circumstances where you can find a gauge in which some of these nonlinearities either disappear or become simple and so on. But they are all special cases. This is not a general statement. So we just got here. So this is the gauge transformation. Now, I talk about curvature. It turns out that the transformation for the curvature is easier than the transformation for the potential. Why is that the case? I claim that under this kind of transformation, the consequential transformation on the curvature goes simply like this. R goes into R plus I T commutator R. It's purely linear. Now, remember the gamma transformation. Gamma, I will forget about the indices, goes into, I think, something like this, plus, I think, like this. Okay? So there is this nonlinear term. I claim now R goes into something simpler. Here, there is no such term. Okay? That is my claim. Now, the first line applies for the rotation. Now, remember, we are doing rotations. The first line applies to even large rotations. T is not small. But if T is small, I expand to first power in T, I get the second line. I will prove this in two different ways. I will do it now in a rather conceptual and heuristic way. And I leave the algebraic way to you as an exercise. Okay, so let me do the conceptual way first to understand why there is no such analogous term. Remember what R is. R tells you if I go along a closed loop, right? I push a vector around a closed loop. What is the end result? The end result of pushing around a closed loop is identity plus something like I. No I. I? Maybe I think. No I, minus I. If this is C, this is eta. For small C, small eta, I go around a loop, then the end result is the vector is multiplied by this operator. And this commutator is basically R. Okay? That was the conceptual definition. So now, what happens if I do the rotation of axis at each point? Now I rotate the axis at every point. So here I rotate a little bit. 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 In fact, everywhere along the path. Okay? So what do I have? I have two vectors here. The original vector and the vector that you get after the parallel transport. So you see, these two vectors are at the same point. Okay, so let me draw it like this. So I have the original vector, call that psi, and then the new vector after the parallel transport, psi prime. And in fact, the relationship is psi prime is equal to this thing times psi. I do a rotation. This becomes a green vector, and this becomes a green vector. And now I want to relate these to these. Okay? So I do the same trick as before. Instead of relating this to this, I do it for. Okay? I do this. But the important point is the following. These two vectors are at the same point. So this transformation and this transformation are the reverse of each other, are the inverse of each other. They are the same T. You see? They are the same T. So if I do this transformation, what do? I rotate this vector back. I do this transformation, and then I rotate this forward. You understand? So I just put an e to the minus it and e to the it on two sides of this bracket. Which means I put that operator on two sides of this bracket, or in other words, I put it on two sides of R. But the key point is these two T's are the same because I am doing the coordinate transformation at the same point. What coordinate transformation I do in the middle of the path doesn't matter because I'm only comparing the two vectors at the beginning and end of the closed loop. Right? So what happens in the middle, I don't care. The vector is the vector. So rotation forward and the rotation back. Remember the picture we had? We had four objects. You rotate back, parallel transport, and then rotate forward. In the case of the connection one form, the rotation back and the rotation forward are at two different positions, x and x plus delta x. The two rotations may be slightly different. And that is how this term comes about. The two transformations are slightly different. But when you talk about a curvature tensor, you are talking about something that happens after a closed loop. So you are comparing two vectors at the same point. Therefore, the rotation forward and the rotation back is the same rotation, the same t in this expression. So there is no derivative of t. That's why R transforms linearly. That's why the statement that R is equal to 0 is an invariant statement. It is a statement which, if it is true in one coordinate system, remains always true in all coordinate systems under all coordinate transformations. And the reason, if you say a vector under parallel transport comes back to the same vector, that is a statement that can be made without reference to coordinates. It's a statement about the vector. It's not a statement about the components of a vector. So that is the heuristic and, in fact, the conceptual understanding as to why the curvature tensor transforms linearly. In Riemann geometry, we say the curvature is a tensor because it transforms by a bunch of matrices sitting in front. The Christoffel one form is not a tensor, even though it carries three indices. Is that okay? Now, this is the heuristic, the conceptual proof. The algebraic proof is sort of more explicit, but actually more difficult to understand, and some miraculous cancellations. So what you need to do is the following. You have an expression for how gamma transforms. In other words, this expression. You have an expression for R in terms of gamma, right? So R is equal to d gamma minus d gamma plus gamma times, right? So just put these two together. On this side, change every gamma by that expression. And check that all the nonlinear terms cancel. And the linear terms simply combine to give this. Right? So that is something that even a mathematics student, undergraduate mathematical student, can just do by brute force. Maybe even Mathematica can do by brute force. I don't know. You don't have to think, right? It's just a matter of manipulating the operators, just knowing a few properties. Right? And you can prove the same thing. And that I leave as an exercise. Okay? I don't want to spend time doing algebra. But you have to understand why you get such a simple result. And the reason is that the curvature is a statement about a closed loop. Therefore, it cannot possibly depend on the difference of the T matrices, the transformation matrices at different points. Is that okay? Okay, so that is a check for you. So check means just do this. Okay, that's a set as exercise, maybe not till later. So that is all I'm going to say about non-abelian gauge theories. A rather abstract introduction. You can't really get to work and compute numbers and compare with experiments until you have also learned the Dirac theory, quantum field theory, and so on. Okay. In fact, the initial work was not all that difficult. You know, 30 long ago? 30 years ago, 70 some years ago. If you know this, and you know the quantum field theory, and you can calculate Feynman diagrams, and you calculate the simplest 4 or 5 Feynman diagrams, just one single loop, then you could have won a Nobel Prize. That is Gross, Wilczek, and Politzer, Nobel Prize, I think 2004 or 04, I think, was calculating what's called the beta function in quantum chromodynamics. and finding that it is negative. You don't even have to know the magnitude. It's just a sign. It's negative. It turns out to have very significant consequences. It's just a matter of calculating Feynman diagrams, right? The first one to do it was actually very simple. Any reasonably good graduate student, if told to do that in those days, could probably have done it. Okay? Not all that difficult. Okay? But there's this quantum field theory that I certainly don't have time to go into in this course. But at least the symmetry aspects, all the important ideas are already here. Okay? Now, the first papers that wrote down the non-abelian gauge theory was Yang and Mills, 1954. When Yang wrote this down, it was not in such elegant language. He did not, at that time, understand that this is really deeply connected to the mathematical idea of connection one forms and curvatures and so on. Right? So he sort of he had some vague feeling and fiddled with the equations and say, if I choose a different color convention at different points, what happens and so on. In those days, it was not even color. He was talking about isospin. Okay? 1954 was way before the idea of color. It was internal isospins. Okay? What would happen? Okay? So the original Yang-Mills paper may be a little bit difficult to read because it is not in this kind of notation. Just like if you go back to the papers of Faraday and Maxwell, you probably find it difficult to read because they didn't have vector notations. Okay? Same idea. So with this understanding, you go back, it's actually relatively easy to understand the color structure of the theory, how the indices, little ABC, how they enter the theory. Right? And that is the part I want to get across. Right. Now, in the remaining time, not today, I mean, I will stop here today. In the remaining lectures, I will deal with two topics. One is I will go back to Yang. So back to the case of U1. And ask the question, what is physical? Because, just to give you some preview, all right? You know that B is physical. All right? That is, you can measure B. A is, in some sense, too much. In the sense that not all of A is physical. You tell me a value of A, I can tell you another value of A, and you can't tell the difference, right? So A contains elements that are not physical. I can change A without changing the physics. Is there something in between? And that is the essence of the next lecture. Now, you may think that B is physical, period. I just have to know B, and that's the answer. And what the next lecture tells you is that you need to know a little bit more than B. Okay? There are situations where an electron, let's say, never experiences any B. It goes in a region where B is always zero. And yet there is a physical effect. Okay? And it turns out what is appropriate is, first of all, it is the loop integral of A. Now you may say, the loop integral of A is the same as flux of B. If I make the flux very small, make the loop very small, that's the same as B, right? If I know all the loop integrals of A, then I know all the B's. But the first answer is that that is not the case. If I look at a domain which is not simply connected, for example, if I have a hole here, right? That electrons cannot go into. Electrons are not allowed into this tube. Huh? Electrons are only allowed to go around this and this. And I tell you ADR here. You see, the idea is the following. Let's take a cross section. Electrons are not allowed to go into here, but there is a flux here, magnetic flux. And electrons can either go this way or this way. Then if I consider this loop integral around this loop, it is not zero, right? Because it encloses a flux. Yet the electron never meets any magnetic field. Electron, everywhere it is, experiences zero magnetic field. And I want to show that there is actually an effect. You can measure an effect. It has actually been measured experimentally. Okay? Because we are talking about a domain of space that excludes this. Okay? So the electron never experiences any magnetic field, yet there is an effect. So there is a subtle difference between this integral and B. And then secondly, I will show that actually it's not even this. The thing that is physical is actually this. That is, that integral does not even have to be unique. Now, unique meaning physical, right? Unique, physical things must be unique. Does not even have to be strictly unique. All I need is that integral with the prefactors to be unique up to 2n pi. Okay? So now that is gradually relaxing what is required to be physical. Or in other words, what is physical is this modulo 2 pi. To say that this integral is 0 or to say that this integral is 2 pi is the same thing. I don't have to give you a unique answer. So I am relaxing, going to take 2 steps and relax what is required to be physical and unique. And the end result of these 2 relaxations is that will allow the theory of monopoles. Okay? That will allow the physics of monopoles. Because if you think about this, if you look only at this level, any monopole is allowed. Because all you say is divergence B is rho magnetic. So any rho magnetic is allowed. Any monopole is allowed. If you look at this, so this is any monopole is allowed. If you look at A, if you believe A is physical, then no monopole is allowed. Because if A is physical, B is curl A, then divergence B must be 0. Right? Do you understand? The 2 extremes. If you believe only B is physical, all you ever have to talk about is B, then any magnetic monopole is allowed. If you believe A is physical, then no monopole is allowed. Because B is curl A, and therefore divergence B is 0. But the actual story is somewhere in between. This is physical. This is more than B and less than A. It carries more information than B, less information than or A. And if you believe this is what is physical, then some monopoles are allowed. And in fact, monopole strengths that go as, I think, n over 2 Planck constant. I think that's right, yeah. Okay? So this is sort of, the correct answer is halfway in between. The physical information is more than B and less than A. And therefore, it's not true that all monopoles are allowed. It's not true that no monopoles are allowed. It's only true that some monopoles are allowed, quantized at these values. All right? And of course, how did this all come about? Comes about because of the idea of phase. This is the phase, right? Okay, and quantization, because this phase is related to the phase of the quantum mechanical wave function. All right, so that is the preview of the issues we will try to address in the next lecture. The lecture after that, I will go very quickly to connect to the theory of Riemann geometry, okay? Because this language makes Riemann geometry actually quite simple. Some of the statements so that you at least know the connection. And then I will also talk about, I think, the mathematical idea of fiber bundles, which actually is also very deeply connected. Right? Okay, so let's stop here.